we have all heard the prevailing narrative dominating the headlines.
Yeah. Every day.
Right, the whole assertion that artificial intelligence is just rapidly encroaching on these highly specialized professions.
Coming for everyone's jobs, essentially.
Exactly. I mean, we know generative AI can write complex code.
It can draft sophisticated legal contracts.
Yeah, generate photorealistic art in seconds. But what happens when you take a generative AI model, you hand it a chest X-ray, and you essentially ask it to, well, play doctor?
It is a massive leap.
It is.
Yes.
And that is the precise question we are tackling today. Because for you, the listener, the person who actively follows these technological shifts.
The learner who wants to cut through the marketing hype.
Yes, exactly. You want to see what the empirical data actually says. And this is the perfect deep dive for that.
Absolutely.
Our mission today is to examine the hard, undeniable facts regarding how generative AI truly performs in the high-stakes environment of radiology.
And we have some incredible new data to look at.
We do. We have our hands on a brand new, hot-off-the-presses research letter. This is from the American Journal of Radiology, or the AJR.
It's a highly respected journal.
Yeah, published just days ago, March 4th, 2026. Okay, let's unpack this because the researchers here, they intentionally avoided using some sanitized, perfectly curated lab simulation.
They absolutely did. And honestly, that methodological choice, it's what makes the study such a crucial reality check for the whole industry right now.
Because things are moving so fast.
Breathtakingly fast. We are in a phase where the capabilities of AI are advancing at this incredible pace, which, it often leads to inflated expectations.
People think it's ready for immediate real-world deployment.
Right. And this study grounds the conversation. It provides direct, really rigorous comparison of how different architectural types of AI models handle a very real, incredibly nuanced medical diagnostic task.
Yeah, the setup for this study is just remarkably grounded.
It is.
So they utilized a real-world data set, 212 consecutive frontal chest radiographs.
And that word is key, consecutive.
Right, these were not cherry-picked examples of, textbook diseases.
Yeah.
These were consecutive scans taken between September and November of 2023 at secondary hospitals across the U.S.
Using a teleradiology service.
Exactly.
Yeah.
So that word consecutive is vital here because it means the AI is being fed the messy, the ambiguous, the borderline cases.
The stuff that represents a random Wednesday afternoon at a community hospital.
Exactly. We're looking at 212 unique human beings, 124 male, 88 female, average age of about 48.9 years.
And no cases were excluded just to make the AI look better.
Right. But the part of the methodology that really stands out to me, it's the blind test.
Oh, yeah.
Feeding an AI a raw X-ray with absolutely zero patient history. I mean, that feels like a massive handicap.
It is a profound handicap, and it's a critical detail you really have to keep in mind as we analyze the performance metrics later on.
Because it wasn't just limited information, right?
No, it was nothing. When the researchers submitted these 212 X-rays to the AI models, they provided the image and nothing else. It was strictly an image-only input.
Wow.
No clinical history attached, no patient background, no physician notes saying why the patient was even in the hospital.
No hints about their symptoms at all.
Zero. And to put that into perspective, a human radiologist almost never operates in a vacuum like that.
Right, they always have some context.
Exactly. Even a basic order will include a simple note, like patient presents with a chronic cough, or patient experienced blunt force trauma from a fall.
Right, and those clinical clues prime the radiologist on what to look for.
Exactly. By stripping all of that away, the AI models were flying completely blind, just relying solely on pixel analysis.
Which makes the performance of our 4 AI contestants even more intriguing.
Especially since they represent completely different approaches to artificial intelligence.
Let's introduce the models. So first up, we have Gemini 2.5. We can think of this one as the generalist.
The well-read friend who thinks they know everything.
That's a great way to put it. It's a general-purpose, large, multimodal model, trained on vast cross-domain data sets.
Right.
It's highly capable across a wide variety of consumer and professional tasks, but it hasn't been specifically bottlenecked into medical training.
And that generalist nature is its defining feature. It understands human language beautifully. It's ingested a massive amount of information about the world, including medical texts.
But it wasn't engineered from the ground up to be a diagnostic tool.
Precisely.
Which brings us to contestant number 2, MedRAX. This is an interesting contrast. This model represents the specialist.
Very different beast.
Yeah, it's a domain-specific model designed explicitly just for the purpose of generating radiology reports.
Right.
Its entire training architecture has been fine-tuned exclusively on medical images and radiologic reports.
And the contrast there is just stark. Mera 2 has a very narrow, highly focused education compared to Gemini's broad worldly knowledge.
It's designed to understand the specific vernacular and the structural expectations of a medical report.
Yes.
Then we get to the models that really push the boundaries of current architecture. Contestant number 3 is Rad.1.
The first of our agentic models.
Yes, the researchers designate this as an agentic model. It's a vision language model trained specifically to answer radiologic questions. But what sets it apart is that it actively leverages a commercially available classification tool called Harrison.ai CXR.
Right.
And finally, contestant 4 is MedRAX. This is the second agentic model in our group. And this one integrates multiple chest radiograph analysis tools along with multimodal reasoning capabilities.
Which is a lot of buzzwords.
It is. The term agentic gets thrown around a lot in tech circles lately, but we should define how it functions practically in a clinical scenario like this.
What's fascinating here is what agentic actually means when you are trying to solve a complex, multi-step problem.
Right.
When you interact with a standard large language model, you provide a prompt, and a single neural network processes that input to predict the best sequence of output tokens.
It's just one cohesive brain doing all the thinking?
Exactly. An agentic model, however, operates more like a project manager overseeing a specialized team.
Okay.
It is an AI system that coordinates multiple distinct software tools to achieve a final result.
So it's farming out the work.
Yes. So when handed an X-ray, an agentic model might first deploy an independent image classifier just to identify anatomical structures.
Like finding the ribs, the heart, the lungs.
Right. Then it might query a separate information retrieval system to cross-reference medical definitions. And finally, it hands all those sub-findings over to a report generation module to synthesize the data into a cohesive, readable paragraph.
Wow.
It tackles the diagnosis by breaking it down and utilizing purpose-built tools for each distinct step of the process.
And that structural sophistication is put to the ultimate test here. You take these 4 distinct AIs, the generalist, the specialist, and the 2 agentic models.
Right.
And you mandate that they write a professional radiology report for these 212 X-rays using just their default out-of-the-box settings.
No specialized prompt engineering.
No iterative feedback loops at all. Once the models generated their reports, the researchers brought in 3 human doctors to grade them.
Real doctors.
Real doctors. And they selected a really diverse panel. Reader 1 was a thoracic radiologist with 1 year of post-training experience.
Okay.
Reader 2 was an emergency radiologist with 7 years of experience. And Reader 3 was a general radiologist with 3 years of experience.
Utilizing readers with varying levels of experience and different clinical focuses, it adds a vital layer of robustness to the study.
How so?
Well, an emergency radiologist looking at a scan in a trauma setting, they might prioritize findings very differently than a general radiologist who is just reviewing a routine physical exam.
That makes total sense. And crucially, these 3 doctors reviewed the AI-generated reports completely blind.
Essential step.
They had zero indication whether they were evaluating a report written by the generalist Gemini 2.5 or the highly specialized Rad.1.
The model identities were entirely stripped away.
Yep, completely stripped away, and the reports were presented in a randomized order. So the first metric they evaluated was acceptability.
The bottom line.
Right. The readers had to make a binary decision. Could this AI-generated report be accepted and utilized for patient care without any modification?
Because if a human doctor has to spend time rewriting the AI's work, the tool completely loses its efficiency value.
Exactly. And the disparity in the acceptability results across the models is just striking. The generalist, Gemini 2.5, performed dismally.
The acceptability rates for the generalist model really illustrate a significant gap between conversational fluency and actual clinical utility.
Yeah, the numbers are rough.
For Reader 3, the general radiologist, Gemini 2.5's reports were deemed acceptable only 16% of the time.
Wow, 16%.
And even Reader 1, who is the most generous grader across the board, only accepted 35.8% of Gemini's outputs.
But we see a massive paradigm shift when we look at Rad.1, our first agentic model. It just completely separated itself from the pack.
It really did.
Rad.1 achieved acceptance rates ranging from 60.8% up to an impressive 75.5% across the 3 readers.
A huge jump.
Yeah. And the other 2 models, Mera 2 and MedRAX, they fell into the middle tier, generally hovering between 21 and 57% acceptability depending on which doctor was grading them.
And that hierarchy is consistently reflected in the holistic quality scores as well.
Right, the 1 to 5 scale.
Yeah. The doctors were asked to rate the overall quality of the reports on a standard scale from 1 being poor to 5 being very good.
And across all 3 human readers, Rad.1 secured a median score of 4.0.
Very solid.
Meanwhile, Gemini 2.5 languished at the bottom with a median score of 2.0. Rad.1 and MedRAX maintained their middle ground position with median scores of 3.0.
Right.
Furthermore, when the doctors were forced to select their single preferred report for each of the 212 radiographs,
The forced choice.
the consensus was overwhelming. All 3 readers selected Rad.1 as their favorite, choosing it up to 66.5% of the time,
And Gemini.
selected as the preferred report in less than 10% of the cases.
See, while producing a report that reads well to a physician is important for workflow integration, the fundamental purpose of radiology is diagnostic accuracy.
Right. A beautifully written report is useless if it misidentifies the pathology.
Exactly. So the researchers evaluated the model's diagnostic accuracy by tracking 13 distinct radiographic abnormalities across the dataset.
Which amounted to 397 specific abnormalities to be found in total.
Right.
When evaluating diagnostic accuracy, we're really looking at the classic balancing act, right? Sensitivity versus specificity.
Yes.
Sensitivity meaning, did the model successfully detect the actual abnormalities present in the scan?
Right.
Versus specificity, meaning did the model avoid flagging false positives in healthy tissue?
Exactly.
Looking at the generalist, Gemini 2.5 achieved a pooled sensitivity of 50.6% and a specificity of 72.5%.
So it's essentially a coin toss on identifying real problems, combined with a highly concerning rate of false alarms.
Yeah, but the performance of MedRAX, the specialist model, offers a fascinating look at model behavior here.
It really does. It exhibited an incredibly low sensitivity of 35.5%.
Meaning it was failing to identify actual medical issues at an alarming rate.
Yes. However, its specificity was exceptional at 96.0%.
So it seems MedRAX adopted an incredibly conservative strategy. Like, it rarely reported a false positive because it was just highly reluctant to report much of anything at all.
That is a very astute observation. When a model is fine-tuned strictly on medical reports, it can sometimes absorb the defensive, conservative language often utilized by human physicians.
Doctors who avoid making definitive calls on ambiguous imaging so they don't cry wolf.
Exactly. The result is a highly specific model that misses a vast amount of underlying pathology.
Now contrast that conservative approach with the clear winner of the study, Rad.1. It achieved a sensitivity of 66.0% and a specificity of 94.6%.
Successfully navigated the balancing act.
Proving to be the most capable at finding the actual abnormalities while maintaining a stringent defense against those false positives.
Right. And the other agentic model, MedRAX.
It posted a decent sensitivity of 63.0%, but it's troubled with a lower specificity of 76.7%.
So is crying wolf a bit more.
Yeah. If you consider the perspective of a patient awaiting a diagnosis, if you're listening with the patient, the data heavily favors the specialized architecture of Rad.1.
If we connect this to the bigger picture, these diagnostic metrics expose a widespread misconception regarding artificial intelligence right now.
Which is?
Because consumers interact daily with general-purpose AI that can eloquently draft essays, summarize complex articles, and converse naturally, there is an assumption that this fluency equates to universal competence.
Right. They sound smart, so they must be smart at everything.
Exactly. But this study clearly demonstrates that a general-purpose AI, regardless of its linguistic sophistication, is currently ill-equipped for specialized clinical tasks.
It's just not there yet.
True clinical utility requires purpose-built agentic architectures that are explicitly designed to coordinate medical analysis tools.
And that distinction brings us to the most concerning section of the research letter. The evaluation of clinical hallucinations.
The make-believe.
Yes. When AI plays make-believe, the researchers introduced a fourth-grading physician for this, another thoracic radiologist with 7 years of experience.
And their sole task was to review the AI reports strictly for fabrications.
Right. And in this context, a hallucination is defined as a definitive statement in the report that is entirely unsupported by the visual evidence in the inputted X-ray.
We are talking about the AI inventing pathologies, or explicitly referencing prior imaging studies that simply do not exist.
And the statistical breakdown of these hallucinations provides a sobering reality check on the current limitations of generative technology in medicine.
It really does.
Rad.1, which dominated the quality and accuracy metrics, still produced hallucinations in 5.7% of its reports.
Which is still a number you want to get down.
Absolutely.
Yeah.
Gemini 2.5 hallucinated 10.8% of the time, and the specialist Naviadu hallucinated in 19.3% of its outputs.
But the statistic that truly stands out belongs to MedRAX, the second agentic model.
Yeah, this is wild. It generated hallucinations in a staggering 53.8% of its reports. In more than half of the cases it analyzed, the model fabricated clinical details. And here's where it gets really interesting, because the researchers didn't merely provide the raw percentages.
No, they showed the receipts.
They really did.
Wow.
Figure 1 in the study outlines specific visual case studies from publicly available datasets to demonstrate exactly how dangerous these hallucinations can be in practice.
Let's walk through them.
Yeah, let's examine case 1. This was sourced from the VinDoctor CXR dataset. The patient in this image presents with a small to moderate left pneumothorax.
Which is a collapsed lung on the left side of the chest cavity.
Right.
And a pneumothorax is a critical, potentially life-threatening condition that requires immediate and precise intervention.
But when the X-ray was processed, both Gemini 2.5 and MedRAX failed to detect the collapse entirely,
Just completely missed it.
generating reports that concluded the lungs were clear of acute abnormality.
Terrifying.
Rad.1 successfully identified the pneumothorax, but it made a severe topographical error. It confidently reported a right-sided apical pneumothorax.
It recognized the pathology but hallucinated its location.
Right, moving the collapsed lung to the completely opposite side of the patient's body.
And from a clinical standpoint, identifying the correct pathology on the wrong side of the body is catastrophic.
How so? Like, practically speaking.
Well, if a physician relied on that report without reviewing the image themselves, they could theoretically insert a chest tube into the patient's healthy right lung,
Oh, wow.
turning a singular crisis into a dual lung emergency.
That is horrifying. But the behavior of MedRAX in this case is even more complex.
Yes.
The model confidently generated the following sentence, quote, "In comparison with the prior study, there is little change in the appearance of a small to moderate right pneumothorax."
Incredible.
It further elaborated that the issue was slightly larger than on the prior study.
The model completely fabricated a fake medical history.
There was no prior study provided to the AI.
None.
It hallucinated an entire clinical past for this patient just to lend unearned authority to its assessment.
And understanding the underlying mechanics of why this happens is crucial for anyone following this tech.
Why does it do that?
Generative AI models are fundamentally complex autocomplete engines. They predict the statistically most probable sequence of words based on the vast data sets they were trained on.
Right, predicting the next word.
Yes. Now, human physicians are trained to acknowledge uncertainty. If a radiologist is unsure, they will explicitly state the findings are inconclusive. They'll recommend a follow-up CT scan.
They admit they don't know.
Exactly.
Yeah.
Generative AI lacks the inherent capacity for doubt. When faced with ambiguity, it relies on statistical patterns. Because thousands of real radiology reports in its training data begin with the phrase, "in comparison with the prior study."
The AI generates that phrase to make its output structurally mimic a highly professional report.
Exactly, sacrificing factual reality in the process.
It is prioritizing the aesthetic of clinical authority over the accuracy of the visual data,
Yes.
which is so dangerous.
Yeah.
Let's look at case 2, drawn from the PatchS dataset. This further illustrates this point. The patient presents with the small right pneumothorax, a small right pleural effusion, and subcutaneous emphysema.
A lot going on.
Yeah, and the highly conservative specialist model, AR2, missed all of the abnormalities, once again declaring the lungs clear.
Staying quiet to avoid being wrong.
Exactly. MedRAX missed the collapsed lung and instead incorrectly diagnosed moderate chronic cardiomegaly, or an enlarged heart.
Right.
But the generalist model, Gemini 2.5, suffered a complete analytical breakdown.
The output from Gemini 2.5 in case 2 represents the severe risk of applying non-medical models to diagnostic imaging.
It really does. Gemini 2.5 invented an entirely fake central venous catheter.
An IV line going into a major neck vein.
That simply wasn't present anywhere in the image. It detailed the exact anatomical positioning of this non-existent catheter.
Just completely made up.
Entirely. Furthermore, it diagnosed an extensive collapse on the completely opposite side of the chest, entirely missing the actual pneumothorax on the right.
Right.
It constructed a highly detailed, highly clinical, an entirely fictional medical scenario.
And that level of detailed fabrication highlights the precise danger we are facing. The report sounds incredibly professional.
It uses all the right big words.
It utilizes the correct terminology flawlessly, which could easily lull a rushed clinician into a false sense of security.
You read it and you think, wow, this AI really knows what it's talking about.
Exactly.
Now, to maintain an objective view of the research, we have to acknowledge the caveats explicitly outlined by the authors.
Always important.
This study is a compelling snapshot, but it's not exhaustive. The sample size is restricted to 212 cases.
Which is relatively small.
Yeah. The scope is limited strictly to frontal chest radiographs, leaving the performance on complex 3D imaging like CT scans or MRIs entirely untested.
Different ballgame entirely.
Completely. The researchers also utilized baseline default settings for all the models, without exploring how advanced prompt engineering might alter the outputs.
Furthermore, the study did not test for intra-model consistency.
What does that mean?
We do not know if asking the same model to read the same X-ray 5 consecutive times yields 5 identical reports or 5 wildly different interpretations.
Oh, right. Because AI can sometimes give you a different answer every time you hit generate.
Exactly. But the most significant limitation remains the image-only constraint.
Right. Forcing the AI to operate without a patient history is an excellent stress test for evaluating raw image recognition, but it inherently diverges from real-world medical practice.
Completely.
A radiologist integrates the visual data with the patient's electronic health record, their lab results, and their prior imaging.
Depriving the models of that multimodal context undoubtedly suppressed their theoretical maximum performance.
It did.
However, until AI systems can reliably parse and integrate that multimodal clinical context without hallucinating fake prior studies.
The image-only baseline remains a necessary proving ground.
Exactly.
So what does this all mean for the immediate future of AI in medicine? You, as the listener, what should you take away from this? We are presented with data showing the immense structural promise of agentic models like Rad.1, simultaneously contrasted with the reality of a 53% hallucination rate from a model like MedRAX.
The fundamental takeaway from this research letter is that generative AI models currently display massive, unpredictable variability in clinical settings.
Massive variability.
The authors emphasize that robust, rigorous, multidimensional benchmarking of individual models is an absolute prerequisite before any of this technology touches a hospital workflow.
You can't just plug ChatGPT into an MRI machine and hope for the best.
Precisely. Healthcare systems cannot view AI as a monolith. A model's ability to pass a medical board exam does not guarantee its ability to accurately read an X-ray.
Right.
Every specific model architecture must be exhaustively validated against the exact clinical task it is intended to perform.
We are undoubtedly standing on the precipice of a massive technological integration in healthcare.
Without a doubt.
The potential for agentic AI architectures to assist human doctors, to streamline workflows and catch subtle pathologies, it's vast.
The potential is incredible.
It is. However, that potential is currently tethered to the reality that these systems can smoothly and confidently invent clinical data.
This raises an important question for everyone looking toward the future of this technology.
Yeah.
We are currently investing billions of dollars in scaling these models to be faster, more articulate, and more comprehensive.
Right.
But if an AI can flawlessly hallucinate a prior medical study to justify a misdiagnosis today, how do we fundamentally train future diagnostic AI to experience doubt?
Wow.
Can we successfully engineer an algorithm to possess the distinctly human trait of recognizing its own limitations, prompting it to pause its autocomplete function and explicitly request a human second opinion?
Rather than just generating a convincing lie.
That is the pivotal engineering challenge that must be solved as generative AI transitions from consumer applications into critical healthcare infrastructure. Thank you for joining us for this deep dive. We hope this exploration provided you with a clear, data-driven understanding of exactly where medical AI stands today, far beyond the optimistic headlines. Keep analyzing the world around you, keep demanding the hard data, and we will catch you next time.